I will begin with a couple of quotations. It's a mannerism of mine. So this is from early 20th century American poet Wallace Stevens, one of my favorites. His poem, 13 Ways of Looking at a Blackbird. I know noble accents and lucid, inescapable rhythms, but I know too that the blackbird is involved in what I know. The poem consists of 13 stanzas, each of which is about a blackbird, and it is impossible to try and make sense of the metaphor of the blackbird consistently through all 13 stanzas, which was part of Stevens' point. But for our purposes, the reason why I think that this is relevant is because the blackbird is a very mysterious entity in the poem, and yet it is deeply involved in everything that we know about dark energy in particular. If one likes, one can think of the blackbird as dark energy for our purposes. The second is a little perhaps harsher. It's from Eric Temple Bell's magisterial History of Mathematics, Men of Mathematics. If a lunatic scribbles a jumble of mathematical symbols, it does not follow that the writing means anything merely because, to the inexpert eye, it is indistinguishable from higher mathematics. Thank you. I knew that was going to happen. I'll hold on to this. Okay. If a lunatic scribbles a jumble of mathematical symbols, it does not follow that the writing means anything merely because, to the inexpert eye, it is indistinguishable from higher mathematics. I trust the sense of this quotation will become clear as we go through the lecture. So because I didn't finish everything I wanted to say on Monday, I'm going to spend the first part of the lecture finishing my discussion of the standard model of cosmology and standard views on what lambda is or may be, the cosmological constant, dark energy, before moving into the more epistemological part of the lecture. So, standard model of cosmology continued from Monday. So recall the summary of the lambda CDM model. The space-time geometry is a flat, spatially expanding FLRW space-time, spatially homogeneous and isotropic. The matter content are various radiation fields, photons and neutrinos, ordinary matter, baryons and leptons, cold dark matter, whatever that may be, the cosmological constant, whatever that may be. And all of these are idealized in our model in lambda CDM as perfect fluids. And lambda's barotropic index is -1. So recall that was the ratio of the energy density to the pressure. And that means in particular that the pressure is extremely negative, which is extremely bizarre for as compared to any other kind of matter that we have real knowledge of. And the geometry matter interaction is given by general relativity, the Einstein field equation. So I will very briefly I was going to discuss the observational support for various aspects of lambda CDM, but in the interest of time, because I also want to talk about epistemology in particular, today I'm only going to focus on the support for the fact that the universe is expanding. And by this I mean not just, I don't necessarily mean the support we have for the universe's being in an accelerated state of expansion, which is what lambda is, what the cosmological constant is supposed to give us, but just the fact that it's expanding at all and not static. As Slava mentioned on Monday, early workers in GR and cosmology, including perhaps primarily Einstein himself, were very much in favor of a static universe, one that was more or less, at least at the largest growth scales, unchanging over time. And there still is some, I wouldn't call it very serious debate, but people still do worry about how much our observations support the idea that the universe is expanding rather than static. And there are real questions about how much the observations can and do support that. So the observational support for the idea that the universe is expanding comes primarily from the galactic Hubble redshift. We measure the redshift of galaxies, and we see that the further away galaxies are, the higher the redshift seems to be, and that gives strong evidence in favor. Now, this is by no means definitive, but it does very strongly favor expansion. People have tried to construct various alternative explanations for why there should be this redshift relation, or even to question the observational conclusion that there is this relationship between distance and redshift, but none of them are really very convincing.
And why does it say that it's not definitive?
Because there are, in fact, because there are. I'll get to that in a minute, but I can very quickly say. Because there are discrepancies in the Hubble measurements, because there are alternative proposals people have made to try to explain why such a redshift, why such a correlation between distance and redshift may appear, even though there aren't, even though the universe would not in fact be expanding. So some people have tried, and people also question various of. These observations are, as I'll discuss later in the lecture, are very, very highly, in a sense, theory-laden. One requires an enormous amount of theory in order to structure the raw observational results, in order to put them into a form that's really directly comparable to theoretical models. And so people worry that that the kind of theory that's being used when structuring the data is begging the question, is building expansion in. So I personally think, and I think the overwhelming majority of people in the field think that these are all problems that can be resolved or have been resolved. But it's still, I think it's still interesting to see exactly what the evidence is that makes us believe that the universe is expanding, and as I'll discuss in a moment, what some possible problems are with that evidence. So the CMB as a function of redshift, it's a fairly straightforward calculation that the temperature of the CMB, as one looks further and further back, the CMB should be hotter and hotter and hotter in an expanding universe. And we can infer the value of the temperature of the CMB by measuring absorption lines from high redshift systems. High Z here means Z is a very common variable used to represent the idea of redshift. So how far back something is as a function of redshift. So high redshift systems, and that primarily comes from the rotational excitation of cosmologically abundant molecules. So time dilation is used. You measure the rate of ticks for cosmic clocks at different redshifts. Primarily what are used are type 1a supernova for this. And again, if the universe is expanding, things at very high redshift, things that we think are very far back in time, their clocks should be ticking more slowly. They should look like they're ticking more slowly because the light that's reaching us, the electromagnetic radiation that's reaching us, from which we infer how fast the processes are going in these systems, is being redshifted because it's moving through the effective gravitational well that expansion imposes. There are also so-called cosmic chronometers, primarily the Hubble parameter from the variation in age of elliptical galaxies by redshift. There's the Tolman test, which if you have an idea of the absolute luminosity, the surface brightness of a galaxy, it should vary as 1 plus z, the redshift, to the power n, where n equals -1 for static and n equals -4 for expanding. The data pretty clearly seems to show -4, not -1. And there are several other less compelling, more unsettled sources of data, sources of evidence in favor of expansion. So in partial answer to your question, I should also say, in the footnote, this reference I give to Lopez Corredora, 2017. So what is the epistemic value of these observations? Well, I think so. There are two ways in which the observations that I mentioned, the sources of observation, the observations themselves, the way the raw data, the raw numbers in the observations are manipulated and structured so as to be put into a form in which they can be compared with theoretical statements. It is there are two reasons why I think that this all constitutes actually extremely high quality evidence. One is that when you take them all together, because they are probing very different kinds of physical systems, and they are probing, even when the studies are made of the same systems, they're probing the results of different physical processes that occur in the same systems. It's a classic example of consilience, which, as philosophers and scientists, you should all know is one of the most powerful properties that evidence can have in favor of theoretical claims. And consilience is essentially when you have evidence that is evidence from independent, unrelated sources converge on the same result. And that is what is happening here. It would seem.
XXVII is the book of Avogadro number, yes?
Yes.
Great.
Yeah. So, in fact, I should have put. So, I mean, the Smith and the Seth that I refer to here is actually relevant for both. I should have put this up here also. So this is a truly extraordinary book. I think without exaggeration, it might be the best philosophy of science book published in like the last 30 years. It's amazing. It's a book in which George Smith and Raghav Seth analyze the Parán's original data for the observation of Brownian motion to calculate Avogadro's number. And they actually go through all of Parán's original data because we have his notebooks, and they do all the calculations ab initio from scratch. They redo all the calculations. They redo all of the theoretical derivations from scratch, and they show that Parán really did have evidence streams from radically different aspects of Brownian motion, from which they were able to calculate Avogadro's number. He was able to calculate Avogadro's number using several different dynamic aspects of Brownian motion, and the agreement was very striking. And so, famously, the evidence that Parán produced by this consilience was so strong that it convinced even the profound doubters of molecules like Poincaré. Poincaré was convinced. Poincaré said, "I now believe in molecules," after Parán's studies. So, yes, for consilience, you should also look at that book. Even if you're not interested in consilience, you should look at that book. It's amazing. But not just taken together as consilience, this long list of data I think is very compelling. Each evidence stream on its own that I mentioned in the previous slide is compelling when viewed over time, because each of those evidence streams aren't just the result of one single set of observations and concomitant theoretical theoretical structuring of observational data to bring it into contact with theoretical claims. Each one has been the result of, over the years, a successive number of different observations made using different instruments that have been employed by different teams of scientists using themselves different theoretical resources, different approximations, different calculational techniques. And over and over, in each iteration of the set of observations made to supply evidence for each evidence stream, the discrepancies that were found in earlier iterations of the observations were corrected both by improvements in instrumentation, improvements in the use of the instrumentation, experimental technique, and improvements in theoretical resources such as approximative techniques used in structuring the data. And it happened every single time that discrepancies and problems in the data in a previous iteration, by taking into account more and more features of the systems being studied, those discrepancies and problems were resolved and brought into closer agreement with theoretical claims. So this kind of method of successive iterated model approximation, where in every step you construct a model, use the model to produce theoretical claims, you use some theoretical instruments, use some theoretical tools to help structure the data in such a way that you can bring it into contact with the theoretical claims. Every single time that was performed and improvements were made, more systematic dependencies in the system under study were being taken account of, the results always improved. This again is very, very strong evidence that what you're observing is, that you're capturing something of real physical significance about what you're observing, and that your theory is getting something very deeply right, as you're able to take into account more features of the system by using more theoretical machinery, and your results improve. That's very strong prima facie evidence that your theory is getting something deeply right about the system at issue. So these two facts together, I think, really support our belief that what we have is very high quality evidence for how the observations are supporting, in this case, the theoretical claim that the universe is expanding. Now, there are some observational tensions, possibly inconsistencies, although I personally don't think so, in the support for expansion. Most seriously, there's the so-called Hubble discrepancy, in which different kinds of measurements of the local Hubble flow, so to speak, which is given more or less by various observational aspects of supernova, versus cosmological measurements, which is given by aspects of the CMB that we're able to measure to a very high degree of accuracy. They seem to give different values for the Hubble parameter. Now, many astrophysicists and cosmologists will say that this discrepancy, this disagreement between measured values for the Hubble parameter, they'll say that this discrepancy is they have a very high confidence level in this disagreement. Now, I personally am skeptical of the methodological soundness of the derivations of the confidence levels that a lot of astrophysicists and cosmologists employ. I'll discuss later in the lecture why it is I think that we may want to be a little cautious and skeptical about these extraordinary claims about, the Hubble discrepancy being supported by, a 5 sigma, 10 sigma confidence level. I'll discuss later my grounds for being a little suspicious of the calculations of those confidence levels. There's another Hubble problem, that the apparent magnitude versus the redshift diagram for elliptical galaxies and clusters actually does better fit a static than an expanding universe, and possibly also the signature of the anisotropies in this apparent magnitude versus redshift diagram. The redshift, as inferred from CMB, there are some discrepancies among studies of different systems, and even some among different studies of the same systems. I mentioned time dilation as evidence in favor of expansion. It turns out that for at least two different kinds of systems, gamma rays and quasars. So I recall I mentioned that what is primarily used in calculating time dilation are the behavior of supernova. If you look at gamma ray bursts and quasars, we don't yet see this time dilation, which is consistent with a static universe, not an expanding universe. In the cosmic chronometers that are used to, again, support expansion, there are rather questionable assumptions, I think seriously questionable assumptions that are made about the homogeneity of the ages of stars in the elliptic galaxies. There are some issues when you compare the angular size of objects versus their redshift. When you have an idea of how big linearly, how big side to side a system is, in itself, and you compare that to the angular distance that we see in the sky, as compared to the redshift, the apparent angular diameter for galaxies shows an inverse relation to redshift, which is what you would expect from a static universe, not the sharper one. I think z to the minus 3 or 4, I forget, that you'd expect from an expanding universe. But there are many theoretical and observational lacuna that need to be filled in to make this and all the others really more decisive. So I'm not mentioning these to make you doubt that we have good reason to think the universe is expanding. I'm mentioning these because I think that to be completely intellectually conscientious, which we should always try to be, whether we're doing philosophy or we're doing physics, we have to be aware of possibly countervailing evidence, even if we are skeptical that in the end, that evidence will survive attempts to improve the observations and improve our theoretical treatment of the observations. I think that the overwhelming majority of cosmologists aren't worried about any of these. And I think they have very good reason not to be worried about any of these, precisely because there are so many aspects of how it is that we are employing theory to make sense of the observations, and so many questions about the quality, the quality, the accuracy, and the precision of the observations themselves, that it's not clear that these results outweigh the much higher quality evidence we have that I cited a few slides ago. Mm-hmm. Mm-hmm.
So on the method of successive approximations, this isn't a case of developing theory to fit observations. I'm just curious because you could have some kind of feedback possibly going on. I haven't read the Harper or those papers, but
no. So the idea is that you have the idea is that you have say some kind of global theory, just to make the explanation simpler. I'll use the example that Harper and Smith themselves talk most about, which is Newton and Newton's derivation of universal gravity. So you have a kind of a global theory, Newtonian gravitational theory, and you have a very complex system that you're studying, the solar system, and you want to construct a model of the system, and you use the theory to make various predictions, and then you discover that there are discrepancies. So, for instance, when Newton in Book 3 of the Principia, when he was deriving universal gravity and then constructing models of planetary orbits to try and show that it worked, what he actually did was he first gave models of each of the planet's orbits individually, and he noted that there are discrepancies, that they don't perfectly match what Newtonian gravitational theory predicted. But instead of saying, my theory is wrong, what he did was he said, but note, if my theory is right, there should be effects of each of the planets on each other. And I'm now going to construct a better model that takes account of these systematic dependencies that I didn't account for in my first very simple model. And in particular, when I take account of Jupiter's perturbative effects on the other planets, then the predictions matched much better. And he was able to do this iteratively several times in Book 3. He like with the comets, with the Jovian satellites, with the moon. Every single time he was able to say, look, if I give you a simple model, it kind of works, but my theory tells me that there are systematic dependencies that aren't incorporated into my model. When I incorporate those now into my model, the predictions get even better. And so that's the method of successive approximations that Smith and Harper talk about. And that's exactly what happens here. I mean, when people first started making these observations of these systems, the theory wasn't under enough control for them to take account of all the dependencies among the parts of the system that theory told us should be in play. And as we got theory under greater control and as we got more and more precise and accurate measurements, we were able to start taking more and more systematic dependencies into account. And every time we did that, the match between theory and observation got better. So, I think that with regard to disagreements, between, for instance, the results of different determinations of Hubble's constant, the Hubble parameter, damn it, and the measurements, I think that, for reasons, again, that I'll discuss later in the lecture, one can really quite reasonably doubt the theoretical structuring of the raw observational data and believe that there are other, as of yet unknown sources of error that are unaccounted for, rather than doubting lambda CDM. At least in our current epistemic state, I think this is the more reasonable attitude to take. But that doesn't mean we should forget about these observational discrepancies. They need to be accounted for in some way or other. And who knows, maybe the more we study them, the better our instruments get, the more control we get over theory, the more systematic dependencies in the systems that we're looking at we're able to account for. Maybe one of them, in fact, will turn out to be a true anomaly, a truly troubling discrepancy. But I think most cosmologists right now aren't worried about it. So if lambda CDM is correct, then based on all these various sources of observation, the composition of mass energy in the universe in the current epoch today is the dark energy makes up about 72% of the mass budget. Dark matter, whatever that is, makes up about 24% of the mass energy budget. And ordinary baryonic matter makes up about 4% of the mass energy budget. So most of the mass energy in the universe right now is in a completely unknown form. This, by itself, this seems to be a very serious problem. And this is exactly why people spend so much time trying to figure out what dark energy is, what dark matter is. Because on the one hand, one attitude to take towards this is this represents a breakdown of general relativity, or it represents a breakdown of the high energy standard model of particle physics. But to me, at least, it's not so clear that we should jump to those conclusions so quickly. Because in a very straightforward sense, there is no failure of general relativity. We use general relativity to calculate these numbers, and we have very high confidence in these numbers. General relativity as a theory never tells us what matter is, because general relativity doesn't care what matter is. The only thing general relativity cares about is stress energy. Remember, the Einstein field equation is, Einstein tensor on left hand equals stress energy tensor of matter on right hand. The stress energy tensor, as a physical quantity, is very much, in a lot of ways, it has many of the properties of energy in Newtonian mechanics. If I tell you that a system has a certain amount of energy, that does not uniquely specify the type of system it is. That tells you almost nothing about any other properties of that system. Almost any other kind of system can have that same energy distribution. And the same thing happens with stress energy. If I just give you a stress energy tensor, there is no way for you to tell me what kind of system it's associated with. Maxwell fields, perfect fluids, dust fields, they can all have the exact same stress energy tensor. They can all have the exact same stress energy distribution. So, scalar fields, the stress energy tensor by itself tells you almost nothing about other properties of the matter field that it's associated with, or in particular, almost nothing about other properties of the matter field that the stress energy tensor is associated with.
Like conservation of energy. It doesn't say thing about, for example, the path, but
Exactly.
it can give you a final position of the object, so
Yeah.
it's pretty similar, maybe.
Yeah, that's right. So if all GR cares about is stress energy, so I know it's not in my mind it's not general relativity's job to tell you what kind of matter there is. It doesn't know and doesn't care. So I don't think that this can be a failure of general relativity. It seems a little more plausible to me that it's a failure of the standard model of high energy particle physics, because if dark energy is a dynamical field of some kind, it is presumably quantum in nature, because we think all matter is quantum in nature. So general relativity, so the standard model of particle physics should tell us something about dark energy, and that's exactly what we'll be discussing in a moment, whether the standard model can do that or not. And the same for dark matter. If dark matter truly is a matter field, the standard model of particle physics should give us some information about what it is. But so far, nothing that has been proposed to explain dark energy within the context of the standard model of particle physics has worked. But we're doing pretty well on 4%, so it's not a total failure. So I'll just discuss a sampling of theoretical and philosophical issues and problems for lambda CDM before moving into exactly what dark energy may be according to some standard stories. So I think one of the most serious in many ways as a methodological issue is there's only one universe. Putting rather speculative ideas about multiverses aside, how can science work without repeatable experiments? You can't, unfortunately, make multiple copies of the universe and make observations on them. And in particular, it makes it very mysterious what likelihood claims mean. Physicists will very often and almost always very blithely make claims such as, well, it seems as though the early universe must have been in a very homogeneous, very isotropic, just extraordinarily homogeneous and isotropic state. How did that happen? It seems incredibly unlikely that the universe would have started in such a perfectly smooth, uniform state. What the hell does unlikely mean there? I mean, you can't. There are no statistics. You can't repeatedly make early states of the universe and see and figure out a probability distribution. So what does it mean when physicists say things like the early state of the universe seems to be unlikely, or for our purposes, as we'll see, the value of the cosmological constant, a lot of physicists think gives rise prima facie to a problem because it seems very finely tuned. It seems incredibly unlikely, they'll say, very low probability that the cosmological constant should have had exactly the value it has. What does that mean? What does a probabilistic claim mean when there is fundamentally one object of interest and you can't perform repeated experiments on it? Mm-hmm.
On the other side, if we have repeated experiments, then we use induction, which is also sometimes criticized. If you repeat experiments, it doesn't mean the outcome will be. So there are actually probabilities that will, sometimes it will happen some unlikely events.
So there are all kinds of problems with probabilistic reasoning, absolutely, and you don't even have to invoke induction to begin to worry about all kinds of probabilistic reasoning. But however bad a lot of the standard problems with probability are, it's still better to have probabilities, to have repeated experiments, to have statistics, and then to say, well, there's some problems, than to have no frequencies, no statistics whatsoever. You're in much deeper shit then.
Yeah, okay, I agree.
And so a second, what are dark matter and dark energy? Well, I've already said a bit about why this is such an important and puzzling problem. Does our ignorance indicate a breakdown in GR, the standard model of particle physics? Well, I've already said a little bit about that. What is the origin of homogeneity and isotropy? I mean, many parts of the visible past universe were never in causal contact with each other. But photons in the CMB in different parts of the sky have no common causal past. But the CMB across the entire sky is homogeneous and isotropic to better than 1 part in 10 to the minus 5. That's a really, really, really homogeneous and isotropic. So how are we supposed to explain this? People often invoke inflation to address this particular problem. I personally, actually don't think inflation solves this problem. Slava, I know, disagrees with me, so he can speak up if he likes to. So, why is the universe so close to flatness? Why is it so perfectly, seemingly just so close to being flat? Because for an FLRW universe to be flat, the matter density has to have exactly what's called a critical value. If it's a little bit above the critical value, the universe will close. If it's a little bit below the critical value, the universe will remain open and continually expand. But in order for the universe to be flat, as it really seems to be, to an extremely high degree of accuracy, the mass energy density has to be almost exactly at its critical value. It seems, again, unlikely that that the mass energy density would be exactly that one critical value, but it seems to be incredibly close. Fine-tuning problem. So again, a lot of people think inflation solves this problem. I don't. Slava disagrees. Why are matter and the dark energy density essentially equal in the current epoch? They are. So even though the mass energy budget of lambda is greater than the mass energy budget of baryonic ordinary matter today, their densities are essentially equal. And people wonder about this. This is called the cosmic coincidence problem. And again, you'll hear people say, it just seems incredibly unlikely that this would have happened. Well, I don't know what unlikely means in this context. Another interesting problem is, in order, our cosmological models aren't just models of our past light cone. They're models of the entire universe. And if our models are right, a lot of the universe is not part of our past light cone. But we extend our ideas about structure formation and what structures and kind of systems and entities there are in the rest of the universe that we have had no causal contact with whatsoever, beyond this cosmological horizon. What is the basis for doing so? Mm-hmm.
Oh, sorry. Erik, can you explain again point 6, that is that the density of matter and density of lambda is the same on large scale? Because I cannot understand very well. Thank you.
So the total amount of energy in that is contributed by lambda is greater than the total amount of energy contributed by baryons. But because lambda is we think kind of uniformly and evenly spread over the entire universe, its density is much, much lower than the density of the baryons, which are all concentrated in stars and galaxies. And so it turns out that those two densities are almost exactly equal, even though there's more of lambda than of baryons. And people are puzzled about this.
But how could they be almost equal if one is 3 times the other one? I cannot understand, because the space is the same. The quantity of space is the same, so the distribution, perhaps in the sense that both are isotropic. No.
Yeah, so we think, yeah, it looks like both are largely isotropic.
Okay. Both are isotropic, no? Because from a quantitative point of view, one is 3 times the other. So in the same quantity of space, there will be 3 times energy than matter, or not?
No. So if you have so it would take me a little while to explain. So can I maybe this will actually come up a little later in the lecture, and I'll be able to give a better explanation for it there. So if we can we hold on till okay, good. So further interesting theoretical and philosophical issues associated with lambda CDM is what exactly is the physical significance and the observability of spatial topology. So in FLRW and lambda CDM, it makes sense to think of, quote unquote, all of space at a given moment of time. That three-dimensional structure has, we think, a unique topology. And recall on Monday, I discussed that one of the ingredients that goes into constructing lambda CDM is an assumption of topological simplicity. We're going to assume that 3 space has a simple topology. It's going to be some combination of the real line, the 1 sphere, the 2 sphere, taken in as a Cartesian product or topologically connected sums. And it's going to be something simple like that. But in fact, both mathematically and it seems physically, nothing actually rules out the possibility that that 3 space has a much more complicated topology. And it actually is known what, for instance, for closed universes, for compact 3 spaces, what the possible topologies are. We can actually give a complete classification. It's got to be of this form, where the K's are just really, really hard to describe, so I'm not going to try. The L's are quotients of the 3 sphere by elements of some nice isometry group of the standard Riemannian geometry on the 3 sphere. And then we have topologically connected sums of S2 cross S. So the most general 3-manifold, the most general topology of a 3-manifold that's consistent with FLRW is connected sums of these elements. Why don't we allow in cosmology 3 space to have one of these more complicated topologies? I don't think that there are any good observational reasons for ruling them out. We rule them out because they're really complex and hard to deal with calculationally and conceptually. So FLRW, it turns out, is unstable against small perturbations as you approach the initial and final singularities. If initial singularities in FLRW are unstable, however, that, for instance, may militate in favor of special initial conditions of the kind that the so-called past hypothesis requires. Although generally we don't use FLRW for very early universe anyway, but it's still an interesting issue to try and understand why it is that we again use FLRW to talk about initial singularities and final singularities in cosmology, when in fact we have good mathematical evidence that these space-time models are unstable against small perturbations as you approach the initial and final singularities. And a final issue I'll mention, just because I find this really, really weird and hard to understand, is that the ADM mass, in general relativity, the ADM mass is a global quantity, which gives you, which in some sense is supposed to represent the total mass energy content contained in all of space at a given moment of time. For closed FLRW models, the ADM mass is identically 0. And that holds almost purely through topological arguments. It doesn't matter what the stress energy content is. It doesn't matter what the topology is. If you have a closed universe, the ADM mass is identically 0. And physicists will generally say things like, well, it just so happens that when you have a finite but bounded space, then whatever matter is present, gravitational binding energy is always negative, ordinary matter is always positive energy, and it just works out perfectly that the two cancel each other out. I find that very mysterious. I would love to have an understanding of why it is that general relativity tells us that the ADM mass is identically zero in closed models. So that completes our survey of lambdas of the standard model of cosmology, lambda CDM. I will now talk briefly about what lambda is or may be on this standard model. I've told you more or less what the standard model of cosmology is in a very, very high overview kind of sketch. Let's now focus on lambda, on dark energy itself, to see what ideas people have about it. So, what is lambda? Well, it's just this thing, And while that is correct, it's not really very illuminating. So let's see if we can do better. The standard story is that lambda is vacuum energy. Lambda is the vacuum energy of the ambient quantum fields that pervade all of space-time. In order to, so I will now tell you I will now tell you more or less what that is supposed to mean. So recall that even in a lowest energy state, in a vacuum state, the uncertainty relations entail that quantum fields fluctuate. And so in particular, they have non-zero expectation value for stress energy. This is the so-called zero-point energy of quantum fields. In general relativity, however, all forms of material stress energy contribute to the stress energy tensor on the right-hand side of the Einstein field equation. And so in particular, they contribute to the space-time curvature. By Lorentz invariance, the equivalence principle, it's very easy to show that the expectation value of the stress energy tensor, the quantum operator for vacuum energy, has the form, the expectation value of a scalar, which is supposed to be the mass, the 0-point mass energy of the field, the expectation value of the fluctuations of the mass energy of the field around its 0-point value, times the metric. Well, that is, and now you can now see why people want to say that this 0-point energy should, if not completely constitute lambda, the dark energy, it at least must contribute to it, because this form, constant times GAB, is exactly the form of the term for the lambda term that appears in the Einstein field equation. And I say it's a constant because by homogeneity and isotropy, this expectation value must be a constant. So let's just to make writing formula and talking easier, let's just define lambda sub v for vacuum to be this constant expectation value for the 0-point energy of all the quantum fields pervading space-time. So it must contribute to the total, what is standardly called the effective cosmological constant in the Einstein field equation, where so lambda effective equals lambda sub e, where that is the, if you like, the pure Einstein cosmological constant, whatever that is, and the vacuum energy. So when you standardly see, when you see the Einstein field equation written down, and it's GAB equals TAB plus lambda little GAB. What I'm calling lambda sub e, the pure Einstein cosmological constant, is just what's normally written as lambda on the right-hand side of the Einstein field equation. But now, the Einstein field equation is going to have this lambda effective term, because whatever the ordinary cosmological constant is, we think we have to add this contribution from the 0-point energy of quantum fields to it as well. So the Einstein field equation now takes this form. So what magnitude should we expect for the vacuum lambda? So consider, we'll just take the absolute simplest possible case, a quantum scalar field of mass m. We'll do a completely standard calculation of the expectation value for the 0-point energy. Just integrate up the energies for the normal modes of the field up to some more or less arbitrary wave number cutoff, because in order to avoid ultraviolet divergences. And so the expectation value of the 0-point energy will essentially be the cutoff to the 4th power over 16 pi squared. If we take GR to be accurate up to the Planck scale, then it's reasonable to set that should not be lambda, that should be nu, I'm sorry. It's reasonable to set nu equal to 8 pi g to the minus 1/2, where g, I'm now explicitly including Newton's constant. This means that the expectation that from this straightforward flat-footed quantum field theory techniques to calculate the expectation value for the vacuum energy of quantum fields in the universe gives us something of the order 10 to the 71 giga electron volts to the 4th power. That's big. That's a lot of energy. What is the observational value of lambda that we see? Well, again, it's quite easy to at least put upper limits on the value for lambda effective, or whatever the total lambda is, from the observed Hubble parameter. By local energy conservation in FLRW, recall I mentioned on Monday that because FLRW is expanding, it's not static, it has no time-like killing field, there's no exact energy conservation. But energy conservation locally holds to an incredibly high degree of accuracy. This expression, the time derivative of the scale factor squared equals 1/3 the scale factor squared times energy, roughly the energy density of ordinary matter plus the effective cosmological constant. This represents energy conservation. Recall that Hubble is defined, the Hubble parameter is defined as A dot over A. So, there's just straightforward integration. A to the minus 2 is going to be roughly upper bounded by h squared. We know that energy mass density of ordinary matter is not much greater than its critical value. This is what I was going on about, that we see the universe to be essentially flat. And this is the value of the critical energy, mass energy density for a flat universe expressed in terms of the Hubble parameter. So putting all these things together, you see that lambda effective is less than or more or less equal to h squared. Today, h, our best estimates for h put it somewhere between 65 and 75 kilometers per second per megaparsec. So lambda effective can't be greater than 10 to the minus 47 giga electron volts based on observation. That's really small. So the straightforward calculation from quantum field theory versus observational constraints on Hubble differ by 125 orders of magnitude. Some people, I think, perhaps rightly, have called this the worst prediction in the history of physics. If you're wrong by 125 orders of magnitude, you're really not doing very well in physics. If you employ some very fancy effective field theory, that's what EFT here is, effective field theory. If you employ some very fancy effective field theory techniques, you can arguably get this number down to about 10 to the 50, which is still pretty fucking bad. But I actually am quite skeptical of those calculations, because they involve, I think, very questionable applications of standard effective field theory techniques. In particular, effective field theory techniques always assume that there is a decoupling of the infrared, the low energy, and the ultraviolet, the high energy. But because you can't shield gravity, because gravity is always operative, so to speak, that assumption actually fails. So a lot of these EFT arguments that are made to try and reduce the value of this discrepancy, I think, are problematic. But nonetheless, even if they're right, the best you get is 10 to the 50, which is terrible. Can't say how terrible it is. So what's going on? What can we do about this? So the kind of simplest, most obvious thing you can do is say, well, there must be an Einstein cosmological constant, and it has exactly the right value to cancel the vacuum energy. But I mean, but again, no, I mean, these two have to match up to over 120 decimal places. So this is a fine-tuning problem. You know, how is it that if there is a an Einstein lambda term, why does it have almost exactly the same magnitude as the vacuum energy, and in fact of the opposite sign? And in one sense, even if this were correct, it would still leave us with the problem that we started with. What is lambda? What is this Einstein lambda that appears to exactly counterbalance the enormous vacuum energy that quantum field theory seems to suggest should be present? So stipulating that there is a perfect Einstein lambda doesn't really do a lot to solve the problem, and just raises further problems itself. The other possibility is to try and show that somehow or other the naive calculation of the vacuum energy for lambda is wrong. Some possibilities for this, well, I've already mentioned one, that because this problem that IR, low energy, is independent of UV, high energy, is incorrect in standard EFT calculations. That's a problem not just for the more fancy EFT moves that are made to try and reduce, 10 to the 125 to 10 to the 50. It's actually, I didn't say so, but this calculation is essentially an EFT calculation itself. It's just a really, really simple, flat-footed one. And the assumptions that go in to simplifying this integral, to constructing the integral in the first place, and simplifying it, use standard effective field theory techniques that, again, the assumptions for which don't always seem to be satisfied very clearly by gravity. So one might think, okay, if we're able to figure out how to apply effective field theory techniques for gravity, then that might resolve the issue. Another problem is that the calculation, both the rough and ready calculation I very quickly went through, and the more fancy pants calculations people try to employ, they are effectively flat space calculations. They're calculations for quantum fields that live in Minkowski spacetime. But the world is not Minkowskian. There's curvature. So to really do a principled calculation for the vacuum energy, we would have to use the machinery of quantum field theory on curved space-time, not quantum field theory on Minkowski space-time. We don't have the framework of quantum field theory on curved space-time, while in some senses fairly well understood, in other senses are not very well understood. So it may be that there are some effects that curved space-time has on this expectation value, in particular on the integral over all of space for this expectation value, that's not accounted for by the flat space-time calculation that we're actually using. No one has any idea what such effects might be, but we can't rule it out. There may be some unknown new physics that we should account for in the calculation, but unknown new physics that's consistent with GR and QFT. Or there may be some unknown new physics that require modifying GR, QFT, or both. The most commonly considered alternatives, the most commonly considered possibilities are: one, promote Newton's constant to a dynamical degree of freedom by allowing it to depend on some scalar field phi. These are called scalar tensor theories. And remember, that's a very radical proposal, because there is no other evidence in favor of taking Newton's constant to be dynamical, except that we're just trying to find some way to resolve this enormous discrepancy in calculations of the vacuum energy that we have problems to be suspicious of in the first place, and what we observe. A second widely considered possibility is to promote lambda, the cosmological constant, to a dynamical degree of freedom, treating it as a scalar field with standard kinetic and potential terms. There are many proposals for how to do this: quintessence, k-essence, tachyon, phantom, dilatonic, and more. Slava has given his own interesting model of this. Again, it's not clear that doing this would solve any problem, because this doesn't so much resolve the discrepancy between the calculation of the vacuum field energy and observation. It just says, let's not worry about the vacuum energy at all. We'll just say whatever lambda there is this other thing. But then you have to tell us why it is that we shouldn't try to incorporate the zero-point energy into the calculation of lambda. Another widely considered alternative is to modify the gravitational field equations. And these are the ones most often considered are so-called FR theories, where to construct them, you add higher order curvature terms to the Einstein-Hilbert action. So a standard way of deriving the Einstein field equation is, let's see, epsilon times is by considering an action of this form, where R is the scalar curvature of the given metric, lambda is the cosmological constant. You vary the action in the standard way, and the Einstein field equation pops out. And also, this is for vacuum, but you might, if you have matter fields, then you will include a matter Lagrangian term also. This will give you the stress energy tensor for ordinary matter. This will give you the Einstein tensor, and this will give you the cosmological constant term lambda times GAB. So one way, so-called FLRW theories say, in fact, scalar curvature is not the only curvature term that should be included in the action. We should also be including terms of the form the square of the Ricci tensor, plus maybe the D'Alembertian of the square of the Weyl tensor, and so on. So you include all these higher order curvature terms and get a new field equation for gravity that differs from Einstein field equation by including the coupling of higher curvature terms to the matter. Another possibility is to modify dispersion relations in the Trans-Planckian regime. And another very popular one is to try to call upon quantum gravity to save the day. So various people working in the frameworks of string theory or loop quantum gravity have developed mechanisms for producing an accelerated expansion that doesn't involve a simple cosmological constant, and seems to avoid the problem of needing to calculate the zero-point energy for quantum fields. But to my mind, quantum gravity programs are even more speculative and less empirically supported than all the things we are considering in cosmology. So I'm not going to, I don't take those very seriously myself. So what are the grounds for adjudication among these alternatives? Well, the standard story is that how we should judge which of these alternatives are most reasonable, most plausible, most pursuit-worthy, it's going to be some combination of their empirical adequacy, other virtues discussed ad nauseum in the philosophical literature, simplicity, explanatory power, so on. It should include some account of their problem-solving adequacy. If I decide to go with FR gravity, will that in fact allow me to solve other problems, not just the problem of lambda? The feasibility of incorporation into other accepted frameworks and theories, and also their testability, which can sometimes it just involves comparative, sometimes just means comparative testability compared to with respect to competitors. And how much each of these, and there are many, many other kinds of epistemic and evidential virtues that people, theoretical virtues, pragmatic virtues that philosophers and scientists consider. And how much each of these is empirical, how much each is theoretical, how much each is evidential epistemic is really quite a complex matter. And how one is going to kind of order them to try to adjudicate is really going to my mind, I don't think that one can give a single answer to that question completely independent of the problem one is actually examining. So it's given how little we know about these alternatives, I think it's extremely difficult at best to apply any of these standard measures of epistemic value. So it's not clear that we're in a position to be able to move forward in any principled way right now in evaluating the plausibility of any of these proposals. As I say, for dark energy, almost none of those are easily evaluated, if at all. So in a very nice review, Burgess remarks, normally such a large disagreement with data immediately spawns many new candidate theories designed to remove the discrepancy without ruining the success of other experimental tests. More experiments are then required to decide which of the new proposals is the one chosen by nature. The same is not true for the vacuum energy, for which there is not even one candidate modification of theory which all agree can provide a potentially viable way to reconcile observations with predictions. We really seem to be in an epistemically deeply, deeply problematic situation with regard to how to evaluate standard calculations of the vacuum energy and compare the enormous values one gets to the really, really, really small values one gets from observation. Okay, so let's move into really more epistemological issues now. I'm going to begin by reading a very, very long passage from a 1955 paper by the great cosmologist Hermann Bondi. Bondi wrote this paper called, is in fact called Fact and Inference in Theory and Observation. He wrote it about the state of astronomy, astrophysics, and cosmology as it was in 1955. It is such a beautiful analysis that it is still, I think, so much of what he says is still relevant today, and he puts it so well that I can't resist giving you showing you this very, very long passage. So Bondi says, It is fashionable nowadays to divide astronomical research into two categories, theoretical and observational. These terms are ill-defined and lack sure philosophical significance, but it is nevertheless true that most astronomers would have little doubt or disagreement on how to classify most published papers. There is undoubtedly a widespread opinion that astronomical theory is by and large airy speculation, that it changes from day to day in its most fundamental tenets, that it is based on ill-considered hypotheses, and that its reliability should accordingly be assessed to be low. By contrast, the results of observational work are, according to this opinion, solid, incontrovertible facts, permanent and precise achievements that will never change and whose reliability is accordingly high. In the present state of astronomy, conflicts between observation and theoretical results continually arise. In the past, credence in such a conflict has generally been given to the observational result, and theoretical advances of considerable significance have been held up by undue reliance on the observations. In such a conflict, it is far wiser to keep an open mind or even to lean to the side of the theory. I'm not done. The purely factual part of the vast majority of observational papers is small. It is also important to realize that these basic facts are frequently obtained at the very limit of the power of the instruments used, and hence are considerable uncertainty. Everything he's saying is exactly applicable to what's happening today. To refer to observational results as facts is an insult to the laborers of the observer, a mistaken attempt to discredit theorists, a disservice to astronomy in general, and exhibits a complete lack of critical sense. Present-day observational astronomy may fairly be called the science of extracting the maximum information from the fundamentally meager data that can be obtained about outer space, an endeavor to stretch both observation and interpretation to the very limit. A similar examination of physical theories in astronomy reveals that their primary basis is very sound indeed, since it rests on established terrestrial physics. In observational work, long chains of inferences are based on frequently somewhat uncertain data, whereas in physical theories of astronomy, though long chains of inferences are also used, they are generally based on much more reliable experimental data that we have from their terrestrial applications. There is therefore no reason to expect any marked difference in the degrees of reliability of so-called theory and of observation, unless indeed it is that theoretical results are of greater reliability. So in normal astrophysics, our theories are under epistemic control because they are straightforward extensions of theories we test and use in terrestrial physics. The Newtonian mechanics of rigid and elastic bodies and of fluids, thermodynamics, Maxwell theory, magnetohydrodynamics, plasma physics, classical and quantum statistical mechanics, condensed matter physics, the basic quantum mechanics involved in computing spectral lines, characterizing the behavior of electron gases, radiative decay, nuclear fusion. These are all theories that we employ in laboratories on the surface of the Earth, and we know how to use them with remarkable power, control, and accuracy. And in this regard, I think Bondi is absolutely right. In cosmology, however, in cosmology especially, related to the kind, when we're dealing with a problem like lambda and dark energy, where we seem to be driven to begin postulating modifications and extensions to the theories that we have under great epistemic control based on our use of them in laboratories on Earth. Bondi's claims, which I think are by and large correct, raise three important questions. Is observational knowledge in cosmology, by its very nature, more or less certain than theoretical knowledge we use to construct cosmological models? As an empirical test, have cosmological theories in the past been shown to be in error more or less frequently than observational results? And is an error in cosmological observation likely to persist for longer or shorter than an error in a cosmological theory? I don't know the answer to these questions. I think it would be an incredibly interesting project to actually try and figure out some principled answers to these questions. I don't think anyone really knows the answers to these questions. But these are questions that we have to confront and have to try and figure out some answer to if we are going to make progress in figuring out how epistemically secure our reasoning and our conclusions are in cosmology. Because in cosmology, and most especially that part dealing with dark energy, we don't know how to answer those three questions at all. And that is because our theories and models are not under epistemic control. And I'll discuss soon what I mean by that claim. I mean, one way of getting One way of getting a grip on what it is, on how it is that when we're trying to adjudicate among alternatives, among proposed alternatives, and we are confronted with the fact that a lot of the alternatives are very, very speculative in the sense that they deviate very far from theories that we do have under some epistemic control based on our use of them in terrestrial laboratories. One way to, I think, to get started on trying to address the issue is to try and figure out what it is that we wish to have in cosmology. Do we want to have something like epistemic security, or do we want to be grounded as far as possible in absolutely secure knowledge, or do we want to open ourselves to the potential for greater understanding, even though it will be based on theories and ideas that are not epistemically secure? Do we begin with epistemically secure matters, or do we rather try and begin with what seem to be clear and rigorous theoretical principles? And there's always a trade-off. But in the field of dark energy, we struggle with both sides. So it's not even clear that trying to decide which sides of this balance we want to favor will actually give us any progress. So I'll spend a little bit of time now talking about some particular epistemological issues that arise with the use of simulations in what is now called the age of high precision astronomy that we find ourselves living in. So in a review of the construction of statistics for stellar population models, which is what forms the basis for a lot of the observations that I've cited so far in discussing our evidence for dark energy, Marison and Strombeck say, in this era of precision astrophysics, interpretive models such as stellar population and galaxy models need to keep pace with the fast observational development. What do they mean? So we have new, very high the fact that we have enormous amount of new high resolution empirical data, but that by itself does not necessarily provide improved scientific knowledge and understanding. The higher spectral resolution we now have, compared to even 10 years ago, for instance, demands concomitant improvements in theoretical models and methods to provide ways of manipulating, structuring, and interpreting the data so as to make it amenable to comparison with theoretical claims and predictions. And likewise, the physical variables that are the target of high-resolution observational programs, the parameters of stellar populations that we don't get from just looking at the spectrum, looking at the spectrum of absorption and emission of various molecules, which is what we actually observe most of the time. The physical variables that characterize these stellar populations can't be measured, can't be calculated without theoretical models that employ significant theoretical resources. And improvements in the observational resolutions require concomitant improvements in those theoretical models and resources. So simulations in particular today play a really powerful and ineliminable evidential role in cosmology. In calibrating data, so for instance specifying the demographics of target populations and determining accurate redshifts using photometry, estimation of physical parameters from data, the generation of a simple stellar population to describe the evolution of spectral energy densities, finding and controlling for selection biases, for instance, misclassification of faint stars as galaxies, providing, in fact, further sources of raw data. People today actually use simulations to construct empirical spectral libraries by theoretically generated ones, in order to make the data large enough to have statistically significant statistics, have statistically significant values. And also to provide detailed models of specific types of astronomical systems. So, for instance, in determining the prior galactic evolution before observation in models of galaxy mergers that initiate quasar activities. So given the fact that simulations are playing such an incredibly pervasive and powerful role, not just in making predictions, but actually in constituting and structuring the data we use to compare theoretical models to, I think we really have to confront some very deep and hard epistemological questions about the uses of these simulations. I mean, evidence must, in some substantive sense, be independent of theory if we're going to use data to test the theory. But if simulations, which are constructed using our best theories, are involved in the very structuring and construction of the data themselves, how can we be sure that there's enough independence in the data and the evidence to constitute real tests of the theoretical models? How are we to guard against the theoretical biases? Determining the scientific conclusions by fitting the current theory, creeping into our inferences and conclusions. And again, I think I was not actually. Yes. Okay. This all becomes even more poignant when one realizes that all the extraordinary high-precision data we're collecting now cannot be interpreted at all without the use of very heavy-duty theoretical machinery such as simulations. The way that high-precision data is massaged so as to be able to have it serve as evidence uses theory in radical ways. Now, I'm not saying this because I want to instill in you doubts about the quality and validity of the data that astrophysicists and cosmologists are using and astronomers are collecting. But I do want, because I think that astronomers by and large are pretty conscientious folks, and they are aware of these issues, and they try very, very hard to compensate for the amount of theoretical pervasion and to control for it. But we as philosophers I think it behooves us to understand the situation and to examine the methods that they're using to try and accommodate and control for this theoretical pervasion. So this, I think, is a really interesting project that some of you may want to consider working on, trying to get a grip on exactly how theory is being used in the construction of evidence that is supposed to test theory. So I'll stop in like 2 or 3 minutes. So testing theories of dark energy requires a very long chain with many links that join high theory to material measures. It's much, much more than just the sudden juxtaposition of, on the one hand, the Einstein field equation or modifications thereof, models of novel scalar fields, and on the other hand, the simple readout of observation. That's not what is happening in cosmology. It is not just theories of dark energy that we are attempting to test. The tests that we're able to come up with test more than bare fundamental laws. They engage the very long chain of theories, solutions, approximations, simulations, numerical calculations that go into the construction of the data and the evidence. The very idea of a test in this sphere is more rightly attributed to that whole chain of links that bind equations and other theoretical structures to the structured observational data themselves, the product of much theory. And this, I think, shows very clearly that the all too common and all too simple philosophical picture of a theory-observation dichotomy is not just too simplistic, it's utterly and fundamentally wrong-headed. The idea of theory versus theoretical terms and observational terms, going back to the logical empiricist and going through von Frossen and still being discussed ad nauseum today, completely misses the really, truly important point of what's happening, not just in cosmology. A lot of the very, very same issues that I'm talking about are involved in the structuring and interpretation of data at the LHC, in particle colliders. So there are several possible goals one may have in structuring data so as to bring observation into substantive contact with theory for purposes of testing. Among them, you may want to try to minimize the amount of theory used, rely only on the most empirically entrenched principles and laws, and so on. You may, if possible, you'll probably want to try and invoke conciliant triangulation using different theories to structure different independent observations that are relevant to the same epistemic goal. Of course, it's not always trivial to spell out what counts as independent here. And also to try and use different observations of the same system or kinds of system to try to control for systematic errors and to winnow out effects of unknown errors. And in the arena of dark energy theories, we are still struggling with all three of these. And I will stop there because it is time to open the floor for questions, although of course y'all should have been asking questions the whole time. But we'll pick up tomorrow.
Yeah, so thanks, Erik, for the lecture. Question?
Mm-hmm.
Thank you very much. This lecture was really wonderful. I have two questions. The first one concerns your dismissive attitude in concerning quantum gravity, in the sense that the problem of dark energy is an enormous problem, how you showed very well, and indeed it seems to me that it could be a guide for making quantum gravity. It is a result, in a sense. For instance, in loop quantum gravity, you know that the cosmological constant is used to avoid infrared divergence, so play a role, in a sense. It's not a good justification, but it's a role inside the theory. So it seems to me that since we are facing a very difficult problem, also something that could be speculative, it is less speculative, is able to take in account this question. This is the first point. The second point is that in a very beautiful book written by a philosopher of cosmology, one of the first, our teacher here in Italy, Silvio Bergia, in the 90s, he make a distinction that is I think is very important. It's very similar to what you are saying now about the question that, in a sense, when you do cosmology, you cannot be completely sure not only about theory but also about data, because Silvio was saying there are a lot of astrophysical observation data, but certain astrophysical data have cosmological relevance, and this cosmological relevance does depend not only from the fact that they are data, but also from our presupposition. So in a sense, there is a very strong theory-ledness of data in cosmology. Thank you very much.
So on the first question, so the reason why I do have a great deal of skepticism towards all programs of quantum gravity is because in the past, when there have been great revolutions in physics, it has almost always happened because there were great amounts of experimental data that could not be accounted for by then existing theory. That not only was in conflict with theory, but no machinations, no sophistications of the theory could seemingly possibly account for it. And it was that data that then existing theory couldn't account for, that was used as a guide and constraint on theorizing in constructing the new theory. We don't have that for quantum gravity. Arguably, except for lambda, except for dark energy, arguably, all of our two best theories, general relativity and quantum field theory, essentially account for almost all experimental and observational data that we've been able to construct so far. And it's not even clear except for the problematic calculation of the 0-point energy that's supposed to give us the vacuum 0-point energy that's supposed to be at least a component of lambda. Both both GR and QFT arguably are not even controverted by anything in cosmology. So we're in the incredibly unusual position, possibly unique position in science, of having our two best theories being able to account for almost all important experimental and observational data. And yet we still feel this urge to construct a unified theory, a theory of quantum gravity, a theory that incorporates both, without any real input or guidance from empirical data. So as far as I can see, we're more or less just shooting in the dark. Now, my claim earlier in the lecture was that I don't think that it makes sense to try and use quantum gravity to solve the dark energy problem, because as far as I'm concerned, quantum gravity programs are, in the sense that they are almost completely unconstrained by experimental observational data, are even more speculative than possible accounts, than proposals people have made, in particular to deal with lambda, because that at least is based on some observational experimental data. Now, it is true, as you pointed out, for instance, with regard to loop quantum gravity, that some programs of quantum gravity do try to employ lambda to solve problems for them. And that's insofar as theorizing about quantum gravity is legitimate at all, that's certainly legitimate. But I don't think that I don't think that kind of use of the cosmological constant in a quantum gravity program will be able to give us any real insight into how to solve the dark energy problem, because it's the way that lambda is used in loop quantum gravity, for instance. It really is just used as a bare constant. It's not derived from any kind of a underlying deeper loop quantum principle. So, that's why I'm skeptical about trying to use quantum gravity to solve the dark energy problem. So, the second question you had about this book, you were talking about this person whose name I'm sorry I missed. Silvio Bergia.
Was an historian and was a physicist, but also an historian and a philosopher of cosmology.
Okay.
He wrote a couple of books, but unfortunately in the 90s, but unfortunately they are in Italian, so in the Anglo-Saxon debate is not so well known, but very well known in Italy.
Okay. So you were saying that he was making some of the same points that I was making about the fact that we not only have theoretical difficulties, but we also have difficulties in how to understand the data that we have and how independent the data is that we have from theory.
Yeah,
But
it's It is very beautiful distinction, epistemological distinction between astrophysical data and a subset of astrophysical data that are cosmological relevant. And when they are cosmological relevant, they are not only astrophysical data, but there is something also that comes from the theory.
I see. Okay, good. Yes. So that sounds exactly right to me. And this is something that I think was implicit in what I said, but I perhaps didn't draw it out explicitly enough because I was going back and forth between astrophysics and cosmology without always being clear on exactly which I was talking about. But so it sounds like what you're saying that this person was arguing. I completely agree with that. Yeah. No, that actually that actually is exactly what I was trying to use the very long passage I quoted from Bondi for, because Bondi was talking both about astrophysics and cosmology, but more about astrophysics. And
Silvio took the same because he knew very well the history of cosmology. He read the same paper probably.
okay, I love this Bondi paper. It's just wonderful, and I think everything that Bondi said in 1955 is almost all of it is still relevant today, and it becomes even. But the fact that the theories we use in astrophysics are theories that we have under great control because we use them in terrestrial laboratories, that gives us, in some sense, a lot more confidence in using our astrophysical theories to understand data and to apply them in studies of astrophysics. But when we then move to cosmology and try and use even the very same data to try and draw cosmological lessons and conclusions, things become much, much more difficult because the theories we now want to use, these cosmological theories, by and large aren't theories that we are able to use and test in our terrestrial laboratories. And so this makes the problem even deeper and more serious. So yeah, I think I'm very sorry that these books are not in English. I mean, I can read Italian okay, but not great. So, but it sounds like I would very much agree with this. I would very much agree with him.
Other question? If not, I think
There's one
Oh,
here?
yeah, sorry.
Thank you very much for such a great lecture. And this is a natural question coming from your lecture. At your today career time, are you positioning yourself as a philosopher, as a theoretical physician, or a practical physician? Because I have a second question, but
Okay.
it's
So
depending on you.
I guess I consider myself with it if you measure by how much time I spend working on different kinds of issues and problems, and I think also if you look at my publication record, I would say I'm about 75% philosopher, 25% theoretical physicist.
Great. Next question then. Do you think that solving this mystery of lambda finally will solve the main problem of philosophy between materialism and idealism?
Oh wow. No, I don't, because it's not clear to me that. I guess it's not clear to me why the problem of dark energy is would be relevant to materialism versus idealism.
Claim that we don't know about matter, how to define matter in your lecture, yeah?
No, I didn't claim that we don't know how to define matter.
Yeah, yes.
I claimed that the Einstein field equation
Yes.
doesn't
Matter, energy,
care about types of
Yes,
matter.
Yes. Okay. And do you feel that can be a solution for this?
No, I don't think so. Again, insofar as I understand what you mean by the opposition of materialism and idealism, I mean, physics deals with matter and space-time geometry. Yeah.
That's physics.
Yes,
Don't mix it.
but I'm speaking as a philosopher now. As a philosopher, on my understanding of physics is that physics deals with matter and space-time geometry. And it's not always, in fact, what I'll be talking about some tomorrow is it's not always easy to disambiguate what exactly is supposed to count as matter and what exactly is supposed to count as space-time geometry. But that, so far as I can tell, that problem doesn't bear on what idealism means, or so. So I'm not sure that I see why one might want to think that it does.
No, for me, it's enough to know with your
Okay.
answers. That is.
Good.
Thank you.
Okay, other question? Yeah.
Just a curiosity. Do you know if the asymptotic safety research program might propose a solution to this problem? If we might have renormalizable non-perturbative terms in the Lagrangian, so maybe it might give corrections to your gravity and maybe it might resolve the dark energy problem.
So the asymptotic safety program in quantum gravity, all I know about it is about its treatment of black holes. So I actually don't know how asymptotic safety tries to deal with cosmological problems. So I'm not competent to say. I'm sorry. Now, if you want to ask me how it deals with black holes, I have things to say. But